Welcome back, everyone. In the previous video, we introduced the basics of AWS load balancing and different types of AWS provides. Now we're going to dive deeper into the most commonly used one, the application load balancer, or ALB. We're also going to explore how SSL and TLS encryption keep our traffic secure and how auto-scaling automatically adjusts capacity to handle changing workloads. By the end of this video, you'll see how these AWS features work together to create a secure, scalable, and highly available application. So what is an application load balancer? The application load balancer operates at layer 7, the application layer of the OSI model. This means it doesn't just route traffic, it understands web requests. So instead of blindly forwarding packets like a network load balancer, an ALB can look at the components of an HTTP request and make routing decisions based on that data. For example, it can route traffic to different backend servers depending on the URL path, like API or /API versus /images. The host name, like api.mysite.com versus blog.mysite.com, or even query strings and headers. This makes the ALB ideal for modern architectures like microservices or containerized applications, where many smaller services can handle specific parts of a larger app. Now we're going to look at ALB integration with AWS services. So ALBs integrate seamlessly with other AWS services, such as EC2 instances, ECS tasks that run in containers, AWS Lambda functions, or even private IP addresses inside your VPC. Each of these backend is grouped into what's called a target group. The ALB distributes incoming requests among the targets in each group and continuously monitors their health. If one target becomes unhealthy, it automatically stops sending traffic to it, keeping your app available without any manual intervention. Next, we have our health checks and target groups. Health checks for ALBs operate at the target group level. Each target group defines a path and port that AWS uses to test whether a backend is functioning properly. For example, it might check /health every 30 seconds, and if the server doesn't respond with 200 OK, that instance is removed from the rotation. This helps keep the traffic flow to a healthy, responsive time. Next up, we have preserving client IP with headers. Since your ALB sits between your users and your backend servers, the servers don't directly see your client's IP address. To solve that, ALBs automatically insert headers such as xforward4 contains the original client IP, xforward port, and xforwarded proto. This lets you log and analyze real client information even though the traffic is going through the load balancer. Next, we're going to do a quick comparison with a network load balancer. NLBs operate at layer 4, the transport layer, which means they focus purely on speed and connection handling. They're capable of managing millions of requests per second with ultra-low latency, making them perfect for real-time systems, gaming servers, or applications that need raw performance over HTTP flexibility. Each NLB can have a static IP per availability zone or use elastic IPs for predictable addresses. And next up, we have our sticky sessions and session affinity. This feature ensures that a specific user is always directed to the same backend instance during their session. AWS implements stickiness using cookies, which can either be application-based cookies created by your app or duration-based cookies managed automatically by AWS. This comes in handy when users store temporary data on a single server, for example, a shopping cart session. However, enabling stickiness can sometimes create uneven load across your instances, so it's best only used when needed. Next up, we have our SSL and TLS encryption, which protects traffic between your users and your load balancer. SSL, or secure sockets layer, is the older term, while TLS, the transport layer security, is the modern standard. In AWS, load balancers use X.509 certificates to encrypt data in transit. You can easily manage these certificates using AWS Certificate Manager, no manual renewals or complicated setup needed. If your application serves multiple domains, you can use server name indication, which allows a single load balancer to handle multiple SSL certificates. ALB and NLB will support SNI, but the older classic load balancer does not. Connection draining, or otherwise known as deregistration delay. This gives active connections time to complete before an instance is taken out of service. So if an EC2 instance is failing or being replaced, AWS stops sending it new requests but lets ongoing sessions finish gracefully. You can configure this timer anywhere from 1 second to up to an hour. Lastly, let's talk about auto-scaling groups, or ASGs. In real-world environments, the amount of traffic hitting your site can change dramatically. Maybe it spikes during business hours and drops at night. So your auto-scaling group monitors this activity and automatically adds new EC2 instances when demand increases and removes instances when traffic slows down. They integrate directly with your load balancer, meaning new instances register automatically and unhealthy ones are replaced. This combination of elastic load balancing and auto-scaling ensures your application always has the right amount of resources, no more, no less, keeping costs down and performance steady. To wrap everything up, the application load balancer, SSL, TLS encryption, and auto-scaling groups work together to form the foundation of modern cloud architecture in AWS. They keep your applications secure, scalable, and available, even under heavier or unpredictable traffic. Thank you for watching. Keep looking out for the next video.